Good morning, all of you. So let's start next topic of this chapter, that is Dalton's law of partial pressure. Dalton's law of partial pressure. So what is the statement of this Dalton's law? So sometimes in IP they are asking this question for 2 marks as a VSQ, right? So see here, what is the statement? The pressure exerted by a mixture of several gases. Pressure exerted by a mixture of several gases equals the sum of the pressures exerted by each gas occupying the same volume. Occupying the same volume. So that is P is equal to F1 by A1 plus F2 by A2 plus so on plus up to Fn by An. So that is P is equal to P1 plus P2 plus P3 plus so on. This is what Dalton's law of partial pressure. So this is very simple. So note and listen. The pressure exerted by a mixture of several gases equals the sum of the pressures exerted by each gas occupying the same volume. Okay, means if suppose in a container you have filled 3 gases, hydrogen, oxygen and nitrogen, and hydrogen exerts pressure P1, nitrogen exerts pressure P2 and oxygen exerts pressure P3, then total pressure exerted by that gas is equal to sum of that all, that is P1 plus P2 plus P3. Okay, so that is what the statement of this Dalton's law of partial pressure. It is very easy. So P is equal to P1 plus P2 plus P3. Next, equation of state or ideal gas equation already we have learned. Then also in terms of Boltzmann constant we are going to learn now. So this is equation of state. Already I told you, equation of state or what we can call it as a ideal gas equation. Okay, PV is equal to MRT, yes or not? But in terms of Boltzmann constant now, how? Let's see. So first point I am writing that real gas behave as an ideal gas. Real gas or real gases behave as ideal gas at low pressure. This is also PSQ. They are asking for 2 marks. When real gases behave as ideal gas, then when at low pressure and high temperature, real gases behaves as ideal gas. Okay, as is missing here. So real gas behaves as ideal gas at low pressure and high temperature. Low pressure and high temperature. Now, ideal gas equation, ideal gas equation. What is ideal gas equation? PV is equal to nRT. PV is equal to nRT. So what is R value? R is equal to, where R is equal to 8.31 joule mole inverse Kelvin inverse. Joule mole inverse Kelvin inverse. Now, if I want to substitute this in terms of Boltzmann constant, then how? So before that, so ideal gas equation I am writing here in terms of Boltzmann constant. Ideal gas equation in terms of Boltzmann constant. So B capital I am writing, okay. Boltzmann's constant. So see now, we know that K is equal to R divided by Na. K is equal to R divided by Na. And if I will substitute this R value, 8.31 divided by Na is Avogadro's number, 6.02 into 10 to the power of 23. Okay. So if I will do this calculation, I am getting 1.38 into 10 to the power minus 23 joule per Kelvin. Joule per Kelvin. If you want to write unit here, you can write if you want joule mole inverse Kelvin inverse, and this is just mole inverse. So this mole inverse and this mole inverse will get cancelled, and you will get joule per Kelvin or joule Kelvin inverse. This is what Boltzmann constant. Now PV is equal to nRT, and we know N is equal to what? Capital N by Na. Capital N by Na. Number of molecules by Avogadro's number. So here, if I will substitute here this, then what I am getting? PV is equal to N by Na into R into T. Now again we know R is equal to what? K is equal to what? R by Na. Here only we did this, right? What is that? R by Na is equal to K, therefore PV is equal to NKT. Therefore PV is equal to NKT. This is what the ideal gas equation in terms of Boltzmann constant. Substitute karo, then R by Na is, but R by Na is equal to K, therefore PV is equal to NKT. This is what ideal gas equation in terms of Boltzmann constant. Okay. Okay, finished. Let's move ahead. Now, next one note point I am giving you. So, note point: 1 mole of an ideal gas at STP. At STP means what? Standard temperature and pressure. Has a volume of 22.4 liters, that is 22.4 into 10 to the power minus 3 meter cube. Keep it in mind, this note point, right? And STP, standard temperature and pressure, means what? Pressure is equal to 1.013 into 10 to the power 5 Newton per meter square. Next, R is equal to 8.31 joule, mole inverse, Kelvin inverse, and temperature T is equal to 273 Kelvin, N is equal to 1. Okay, right? So this is what STP case, or whatever this volume is for this case. Okay, so let's move for next topic now. Next one is relation between pressure and kinetic energy. Very important. Relation between pressure and kinetic energy. Okay, so see, now we know pressure P is equal to 1 by 3 m n by phi, this is volume, into phi RMS whole square. That is equal to 1 by 3 capital M divided by phi into phi RMS whole square. Let us suppose this is your equation number 1. Next, we are having pressure P is equal to, wait, I will give next of this after this equation number 1, not this. Okay, after this now, 1 by 3 m by v you got. So this is m by v is what? Rho into v RMS whole square. Now you can call it as equation number 1. Okay. Now after this, energy E is equal to next one, E is equal to 1 by 2 m by v into v RMS whole square, that is also equal to 1 by 2 into rho v RMS whole square. Call this equation number 2. Now from equation 1 and 2, from equation 1 and 2, if you will see, you will get pressure P is equal to 2 by 3 times the energy. Is very, very important relation. Okay. If we will multiply with this, just transfer this from this equation 1. If you did not understand how you got this, you just see here how you are getting. From 1, you can write like this: 3p is equal to rho into v RMS whole square. And here this side you can write 2e is equal to rho into v RMS square. And you see now this left hand side, right hand side is same. So I can 3p is equal to 2e, and therefore you will get p is equal to 2 by 3 e. Yes, you can see this. Those who did not understand how you got this relation. Okay, so note down. So let's move ahead. Next one. So therefore, the pressure exerted by an ideal gas, therefore the pressure exerted by an ideal gas pressure exerted by an ideal gas is numerically equal to is numerically equal to 2 by 3 of mean kinetic energy that is we got for this P is equal to 2 by 3 hai na? In the previous page you can see. So this is what I am writing in sentence. So you can write here on the next page, or that is just continuation. Below that we can write. The pressure exerted by an ideal gas is numerically equal to 2 by 3 of mean kinetic energy per unit volume of the gas. Mean kinetic energy per unit volume of the gas. And therefore PV is equal to 2 by 3 into E total. Why? Already you got P is equal to 2 by 3 times E. But this E is what? This E is what? Energy per unit volume. Understand? Energy per unit volume. So therefore P is equal to 2 by 3 into E total divided by per unit volume. So this volume when it is going here, so PV is equal to 2 by 3 into E total. Got it? That's why you are getting this expression. Got it? Okay. Wrote down. Okay. Okay. Finished. Just go through this carefully. Whatever we have seen today, right? So note down properly, and we will stop here for today. Bye.